So this is our last set of notes in our second module topic on limits. Just a quick recap before we do topic 4. Topic 1 and topic 2 were basically introductions to limits, kind of what the concept is, working through the limit rules. We're going to be using those limit rules a little bit more today in today's topic. The last video you should have watched on topic 3 would have been, in my opinion, as I probably said during the video plenty of times, I think it's one of the most fundamentally important things that we're doing in this course, where we talk about how to use our limits and how to use that to try to calculate the slope of a tangent line. And it has so many applicable uses in the sciences. And I even mentioned, even in economics, we talk about rates of change. Anything that involves a rate of change, like something that has a fractional value where you need to find a rise over run as slope of something, that can be very useful. Anyways, today is the last topic, and this is going to seem a little disjointed because this really has nothing to do with yesterday's topic, and yet it still has a lot to do with limits. I'm going to show you another place where we can use the concept of limits in order to solve a problem. This actually involves solving a type of question that you would have encountered in Math 30-1. So for those of you who I know who are taking the course at the same time, you may find this actually be useful when we get to the concept of trying to know what the end behavior of certain graphs happen to look like. So anyways, let's get started on our notes for the day. And like I always suggest, have a list ready of questions to ask me. Pause, stop the video when you need to. Rewatch it if you need to. You can watch it on fast forward if you really want to as well. I know that's an option. One thing I've been playing with recently is I discovered that YouTube has this thing where it throws on subtitles. So maybe you even want to throw those on, although it's not always perfect. So, okay, this is recapping a topic from, it's actually something that we do in Math 20-1, the idea of series and sequences. Again, this is going to seem disjointed because it has very little to do necessarily with kind of what we've been doing recently. It's just this is a good place where limits can be applied. It can be applied to sequences and series. And so let me start off with just an example. Let's say I gave you a list, 2, 4, 6, 8. Hopefully you'd recognize that this is a series, or this is a sequence actually, where we seem to be adding 2 every time. If I were to give you 2, 4, 8, 16, this would now be known as geometric because you're multiplying by 2, right? Here you're adding by 2. This is known as arithmetic. If you multiply by 2, it's known as geometric. And currently they're sequences just because they're just it's a pattern that we have. So hopefully you're kind of familiar with this concept of the idea of you have a pattern. And often what we'll do is we'll just label the first term, like this would be, I've lined them up here. In both patterns, my first term, T1, was 2, and then my second term was 4. Then my third term, in one case, was 6, the other one was 8. And then eventually, we sometimes write this notation here where NTN, this is the nth term. Really a way of us describing an unknown term. Somewhere in the future, we're going to have a term that we don't know what it is, and it's a way to notate that. So hopefully this isn't new here. I want to start off with an example of something that you maybe have seen before here. Let's list the first 5 terms in this sequence that's defined by this terminology. So if this is not new terminology, then hopefully I can help introduce it well the first time here. But hopefully this even makes intuitive sense. Tn is kind of like your y value, and your 1 over n is like your x value. Or another way of looking at it is this is like f of x and 1 over x. No, it's all very similar notation, just a different style. This is basically saying we want to know a term in the future based on an unknown number of terms in the future, an unknown variable, like n is your variable, kind of like your x is your variable. And the equation we're going to give you is it's 1 over n. So, for example, if I wanted to find T1, the first term, well, that would be 1 over 1, which would be 1. And then if I wanted to find term 2, well, that would be the second term, so 1 over 2, which is a half. And I don't know why I'm writing this a second time here. That's kind of silly, because term 3 is going to be a third, and term 4 is going to be a fourth, and term 5 will be a fifth. Right, hopefully that makes sense. And I mean, if we wanted to extrapolate this and keep going further, T100 is going to be 1 over 100, right? That'll be your 100th term is 100th, right? So the question I asked here is, what's happening to these terms as n gets larger? And we've experienced this before in so many places in math. I mean, one is just even knowing what this graph looks like. A 1 over n graph, or a 1 over x graph, has roughly that sort of shape to it, a reciprocal shape. You know, there is this section over here as well, but I don't actually care about that. I just want to focus on this section right here. What happens is your x value, or n, I don't really care what letter you pick, but what happens is your x or n value gets larger. What's happening to your y value, or your tn value? And hopefully you'll know that it's getting smaller. Really what it's doing is it's getting closer to 0, right? It's getting closer and closer to 0. But it's never actually going to touch 0, right? Like, that's the whole point of this asymptote. Asymptote. Hopefully you know that word. The idea that there's like, we usually do what, like dotted lines? There's a dotted line here at y equals 0, which is actually impossible to achieve. Y will never be 0. Even if you picked x as 1,000,000, well, then your y would be 1 over 1,000,000. That's actually not 1,000,000, that's 1,000,000. Right? Will it ever actually equal 0? Well, no, it won't. And so this is where limit notation comes in, is we can actually calculate the limit as x approaches infinity. This is a kind of our first main concept here then as well. What is it getting close to? I know it doesn't actually equal 0, but wouldn't this then basically, isn't that what this proof would be, is that as your n value gets exceedingly large, I know on its own, if I didn't put this notation right here, if I didn't include the limit notation, and I said, you know, let x equal 1,000,000, right, that wouldn't actually equal 0, because it would equal 1 over 1,000,000, right? But that's where limits can come in. That's the overlap here, is that what if we just consider this to be getting basically as close and close to infinity as possible? We want this to get as large as possible. What is it getting close to? Hopefully you'd agree. Well, isn't it getting close to 0? Again, that graph. Isn't this graph, as your n value keeps getting further and further, right? As n is getting close to infinity, like an impossibly large number, the limit would be 0. Right? So we can actually do that with a different type of graph. I want to change up the way I write this here. This is the kind of problem that you might have been asked in Math 30-1. Now, we didn't notate it like this. The notation would have been different. You might have been asked this equation, y equals x over x plus 1, and the question might have been, what is the horizontal asymptote? It's kind of a similar question to that. Let me just graph this here with my graphing calculator. If you were to go to your graphing calculator, now every teacher is going to show you this a little differently. So, I mean, here's how I might show my students, just one option. We're going to graph this thing right here. We'll go to Zoom 6. And we want to take a look and see, well, what does it look like it's getting closer and closer to? And it looks like right along here, it looks like there's an asymptote right here. Definitely there's one vertically, right? The vertical one is at -1. Hopefully you're all aware that -1 is not valid for x. But for y, you want to figure out what that is. And one thing you could do is you just go to your table. And you could just start scrolling through your table and start looking at what it gets close to, 0.8s, 0.9s. You know, one downside to this is that you're keeping pressing down for forever. That's ridiculous. Another option is you can go set your table, and rather than it's set at 15, maybe I'll start it at 100, and then go back and see, oh, now it's up to 0.99. And I set my table and make it go to 1,000. That's getting larger, right? Now it's 0.999, right? And eventually, you know, logic would indicate that, well, you know, if I make this get close to infinity, I'm going to make this the biggest number I can. I just keep typing in zeros here. And then I go to my table. Eventually, your graphing calculator craps out. It just says, I can't handle writing 0.99999 repeating. And it finally actually just goes to the number 1 here, right? But will it ever actually equal 1? No, I don't believe it will. I don't think it's actually possible to. I can even prove why it can't equal 1. If you have the equation y equals x over x plus 1, and I try making y equal to 1, watch what happens here. Well, now if I try to solve for x, you're going to want to kind of cross multiply the x plus 1 to the other side, giving you x plus 1 equals x. And this is like, we have a name for them in university, and I'm blanking on it. It's the opposite of a tautology. A tautology is a statement that is always true. This is a statement that is never true. There is no way that x plus 1 can equal x. This is an impossibility. One way we'll even recognize this is that if you try subtracting x from both sides, you've somehow ended up proving that 1 equals 0, which again, it cannot. So anyways, I got off track here. The concept here is that 1 seems to be what this is getting close to. Right? So we could actually say here, to answer this question here, we can actually find this limit just using a graphing calculator. We can find that the answer is 1. Right? And I mean, maybe this even makes sense if you just test some numbers. Let's just, it says n is approaching infinity. Now, in our previous section on limits, we would plug in a number if we could. But like if this was 2, we'd just plug in 2. Or if this number right here was 100, I'd plug in 100. But infinity is not really a number that you can plug in. You can't just make it infinity over infinity plus 1. That doesn't really work that way. But in lieu of that, I mean, one just kind of basic method I could use is just try a number like 1,000 over 1,000 plus 1. 1,000 is pretty large. I know it's not infinity, but wouldn't this give you 1,000 over 1,001? Isn't that going to be pretty close to 1? You ever seen that symbol before? It didn't draw it very nicely. It's like an equal sign. Let me do it better. It's like an equal sign with a little squiggly over top. It means approximately equal to. It's about 1. All right, let's say I didn't use 1,000. Let's say I used even larger number. Well, whatever that large number is, it's the exact same thing, and 1, which again is going to be approximately equal to 1. It's not going to be 1. It's going to really be 0.99 repeating, as the number gets larger, but it's close to 1, right? So, yeah, like I kind of mentioned earlier, you have done this before. At least you should have in 30-1. And for those of you who are, I know in my school, who are taking 30-1, when we get to the concept of wanting to know what a graph looks like, and we know that there's an asymptote, like say right about here, if we know that there's going to be an asymptote right about here, what I'm about to show you now is an algebraic way of calculating it. Because what I don't want you guys doing is what I just did. Don't plug in the number 1,000 and 1,000,000 and guess and check. That's not really solid algebra skills. You're not building the skills you need, right? Don't use your graphing calculators, right? I mean, it's not a bad way. Pardon me. It's not a bad way at first for me to kind of show you how this is supposed to look a little bit and to help build some ideas. But that really that's a poor. It'd be poor teaching of me to let you get away with that, because there's no way you're going to get away with that in university. They want you to get the bigger concept. So here's the bigger concept. We've actually discovered that there's kind of a property here. If you have 1 over n, like 1 over x, and r, let's say you even have it to the power of an exponent, like say 1 over x squared or 1 over x to the 7 or anything along those lines. Any of those graphs, they all kind of look the same way, where the graph just continues to get shorter and shorter towards the axis. We've discovered that there's a property where we can use this property here and say that it's equal to 0. So if you ever see this, we can just replace it with a 0. And that's what we're going to do on our next couple of slides here. So my hint is we're going to use some limit laws, which is why we learned limit laws a little while ago. And maybe you, at the time, you thought, man, these limit laws are kind of dumb. But we're going to discover that they're actually really useful in this next section here. Okay. So let me show you how this example looks. And you're going to get quite a few like this on your assignment. We're going to try to figure out what this looks like as n approaches infinity. Right? Or another way of thinking of it, which we're not going to do this anymore, but this is like the graph of x squared minus x over 2x squared plus 1. And my question here is, as this graph does whatever it does, I'm asking you, where does it kind of level out at as the x values approach infinity? Right, if we could look at it on a graphing calculator, what's happening to it way off the screen over there, right? Which usually means that there's some sort of asymptote. Okay, so ignore the y equals stuff. Let's use our limit rules. One of our limit rules says that things that are divided, well, you can apply the limit to both the top and the bottom. So I can apply this limit to the top, and I can apply this limit to the bottom. That's one of our limit rules. All right. Another one of our limit rules says that if you have things that are added, you can apply the limits individually. So you could say the limit as n approaches infinity for n squared, and then you could minus a limit as n approaches infinity for n, and then divide that by a limit as n approaches infinity for 2n squared. And you could add the limit as n approaches infinity for 1. So I haven't actually done anything too crazy yet. I'm just applying limit rules to things. And essentially, I'm just saying that every single thing gets its own limit. Now, if we can find a way to make this equal to this property right here, 1 over n to the r, I can replace that with a 0. So if I had a 1 over n to the r, I could do that. Unfortunately, I don't. I have a whole bunch of n squareds and n's and n squareds and a constant term. I mean, right off the bat, this one right here, by the way, the limit of 1 as n approaches infinity, by the way, if I wanted to, I could just replace this with a 1, right? Because really what happens as n approaches infinity on a straight line at 1, think of a graph, right? You have a graph and you have the straight line across at 1. What's its behavior going to look like at infinity way over here? Well, isn't it still going to be 1? So, anyways, let's show you the trick here, though. Okay. The trick is actually, I'm going to do a little bit of algebra a little bit earlier in the scenario. You know how you're allowed to do the same thing to the top and bottom of a fraction, and it doesn't change the fraction. Like, for example, I could times by 2 over 2, right? That's like times by 1, right? So that doesn't actually mathematically affect the expression, right? If I multiply by 1 over 1, or if I multiply, you know how we do conjugates? You multiply by, like, 4x plus 1 over 4x plus 1. No, that doesn't actually affect it. I'm going to use a similar trick here, only rather than dividing both sides of the equation, multiplying both sides of the equation, I gave the trick away here. We're going to divide both the top and the bottom of the function by the same value. And the rule here is you use the largest exponent you have. So since this guy right here, the largest exponent is n squared, we are going to divide the top of the fraction by n squared, and we're going to divide the bottom of the fraction by n squared. Now, doesn't that actually really accomplish the same thing? If you were to divide by 2 and then divide by 2, doesn't that just take you back to where you started? I mean, check it in your calculator. Take any number, divide by 2, and then divide by 2, which really the divide by 2 really means multiply by 2. So mathematically, this is, we haven't changed anything. We're just messing around with this a bit. Here's what this means then. This now has been divided by n squared. This one's been divided by n squared. This one's been divided by n squared. And this one's been divided by n squared. Well, watch what that gives us. Okay, I still am writing limits out for everything. I haven't done anything. I haven't substituted yet. But what's n squared divided by n squared? Well, it's 1. What is n squared divided by n divided by n squared? Well, that's 1 over n. What is the limit? Let's see, write the limit here. What is 2n squared divided by n squared? Well, it's just 2. And this one right here, I can't actually do anything. I just have to leave it as the limit as n approaches infinity for 1 over n squared. So hopefully you got that step. If not, rewatch the little section here, because that was a big one. Because now here's something really cool. What is the limit as n approaches infinity for 1? And the answer is 1. You have a straight line at 1, and n is getting infinite, but the thing was 1 the whole way through. That's a 1. And this guy right here has the same property. That's a 2. But here's what we just talked about here. What is the limit as n approaches infinity for 1 over n? And the answer to that is, this is actually being replaced by a 0. Limit at all. This whole thing right here is equal to 0. And this one right here actually has the same property, because really 1 over n squared, by the way, is really, I could just write this as a brief aside, 1 over n squared is 1 over n times 1 over n. And really that limit would apply to both of them. That limit would apply to both of them, right? Except this limit right here is 0, and that limit right there is also 0. So really 1 over n squared, I mean, really think about it. If you did 1 over 100, well, 100 would now become 10,000. 1 over 10,000, it's getting really close to 0. Well, now I don't need my limits anymore, because this one right here, the limit's no longer necessary. This one right here, the limit's no longer necessary. And then for these ones right here, I just used my new property, and so that they're now equivalent to 0, I'm replacing the whole thing with 0. So my final answer is this thing must limit out at a half. If I were to graph it, I don't know what the graph looks like, but that graph must start limiting out at a half. Now, the larger that I make my numbers, they seem to converge at a half. So I'm going to give you a lot of questions along these lines. The trick then is you divide all of your terms by the largest exponential value you have. So watch that again if you need to, and then ask me questions later. Okay, another example here. What if I were to give you -1 to the n? And in this particular example here, I don't have any sort of fancy proof. I just want to talk about what this would look like. If I were to give you -1 to the n, some people think that just means that you have this graph right here where you have -1 right here. But that's not actually how it would work. Let's just consider a table of values. If it was -1 to the power of 1, that would give you -1. -1 to the power of 2 would give you 1. -1 to the power of 3 would go back to -1. -1 to the power of 4 would give you +1. -1 to the 5 would give you -1. Hopefully that's clear as to why that works, right? Because every time you times by another -1, it flips it positive, negative. And it means that you actually have a graph that would look like this, where depending on whether the exponent was even or odd, it would basically alternate back and forth between being +1 and -1. Which means that we just have a general rule here. If I try to give you a negative number as like the base of your exponent, there is no limit. The limit does not exist. We can't even work this as a function. This is, to some degree, kind of like an exponential function. This is like y equals -1 to the x. And when we can't even graph that, it doesn't really work that way. So. Another one that we've talked about, though, is a similar exponential function. What about 1/2 to the x? This graph works actually really similarly to the 1 over x graph. Now, the 1 over x graph actually works right there in that quadrant and in this quadrant right here. That's what the 1 over x graph does. However, the 1/2 to the x graph, if you've done your exponential unit, looks more like this. It actually comes from this quadrant here, goes through an intercept of 1, and then comes down. So it doesn't have the exact same graph, but it has a similar property right here. It still has that asymptote, or as it keeps getting smaller and smaller, it keeps getting closer and closer to 0, right? And maybe you've seen a proof for this before. Oops, too far. If I give you 1/2 to the 1, you have a half, right? If I give you a half squared, it would now be a quarter. A half cubed would be an eighth. A 1/2 to the 4 would be a 16th. And hopefully you see that these values are getting closer and closer to 0. So I have another limit rule for you. If you have a 1/2 to an n, that's equal to 0. Now, we actually have a rule that's a little different here. The way they phrase it on a lot of textbooks, and the one I'm going to give you, is that if you have r to the n, it's equal to 0, with the parameters that r has to be less than 1. But I'm throwing an absolute value in here. Here's what this means. If this guy right here is like, say, 1/2 to the n, that'll work. If you have 1/3 to the n, that'll work. If you have 1 over 7 to the n, that'll work. The absolute value means it could even be 1 over 7 and a negative. Okay, that'll work. It could be -1 over 10 to the n. That'll work as well. But it can't be a number like 2 or 3 or 4. And I can explain that one here. If I were to give you 2 to the n, we need to talk about what that graph looks like. As an exponential graph, that graph just grows and takes off. It does not limit onto a certain number. It just keeps growing bigger and bigger and bigger. What we need is a graph that these first ones right here, what ends up happening is they grow smaller and smaller, and they get closer and closer to 0. The other ones I'm working with here, if I were to give you negative, like say 1/2 to the n, what ends up happening here, it's different than -1. Do a table of values here. If n was 1, the first term would be -1/2. I'll do it as like a sequence now. The second one is going to be +1 over 4, then -1 over 8, then +1 over 16, then -1 over 32. I'll just pause for a second here. Hopefully you can consider why that would work that way, right? Here, to the power of 1 just leaves it the way it is. Here, when you square it, though, it makes it positive. Right? Every other one is going to be positive. Now, as a graph, it kind of does that same hopping up and down thing that I showed you a few minutes ago, only when it hops up and down, it actually goes from negative a half, I'll put that about here, to negative a quarter, positive a quarter, to negative an eighth, to positive a 16th, to negative 1/32. You can see how it's kind of like, although it does jump up and down here, it's getting closer and closer and closer to the axes. So it actually can work with a negative number as long as the base negative number is less than 1. So this only works if you have, think of a number line. If you have from negative 1 to 1, non-inclusive, all of the numbers within there will work. Okay. There is one more exception as well. If this was 0, then you don't even have a number to work with, so we usually don't bother with that one. So this is actually a famous paradox. It's like a thought experiment, and I might have even described this before in a video. This is Zeno's paradox. The idea is basically a man standing in a room has a rule. He cannot walk to the wall. What he's allowed to do, though, is he's allowed to, on order, walk half the distance there, and then half the remaining distance, and that's what he's allowed to do. He's allowed to do half at a time. Well, I mean, functionally, at a certain point, you're all the way to the wall, right? Like if I were to draw this out here, here's the man, and here's the wall, right? If I were to, draw him again, well, now he's halfway there. And if I pick him up even, he's halfway there, halfway there, halfway there, halfway there, halfway there. He may never actually officially be at the wall, right? But essentially he's there, right? That's the concept here, is that what you're really doing is you're summing up an infinite number of smaller distances, right? The first time he goes, let's say this is 10 meters away. The first time he goes, he would have traveled 5 meters, then 2.5, then 1.25, then half of that, half of that, half of that. You're really summing up many smaller distances. And you may have seen this before. I want to relate this back to the start of our section. This is back to something you would have worked on in Math 20-1. The idea of some of these recursive formulas for Tn and Sn. It's been a while since you've used these. It's a grade 11 curriculum, but hopefully this rings a bell. These sorts of formulas where A is your first term, R is your ratio, and then N is how many terms in the future you're looking for. This Tn right here is a formula that will give you basically any one term you're looking for in the future. And this is a formula here, Sn, that will give you the sum of all of the terms added together. And so I'd like to now finish my lesson by showing you a few examples of how we can use limit notation with these sorts of formulas. So let's use the example I just had there. Let's say that the formula is 1/2 plus 1/4 plus 1/8 plus 1/16. Hopefully you get the pattern here. It's 1/2 to the n. Right? That is your general term here. You're doing 1/2, and then you're doing, well, the 2 is getting multiplied by, the 2 is the exponent to a certain number, right? The first one, this is 2 to the 1. That's 2 to the 2, 2 to the 3, 2 to the 4, right? What I want you to do is add them up. So your first term is just 1/2. We're done. That's it. That's all we got, right? S2 means sum up the first 2 terms. So you have to take a half and add a quarter. And hopefully you're fairly good at doing those fractions in your head. That's 3/4. Well, then term 3 is 1/2 plus a quarter plus an eighth. Right? And if I do that, 1/2 plus a quarter plus an eighth, well, I just did it as 3/4. That's what the first 2 equal, right? And if I add to that an eighth, another way of approaching that would be to say that you have 6/8 plus 1/8 is giving you 7/8. Right? So what I want us to do now is we're not looking for necessarily what this function gives just on its own, but I want to consider what we're adding up all these numbers to. What is the sum of all of these numbers? What if I were to do the limit as n approaches infinity for s infinity? What if I were to do 1/2 plus a quarter plus an eighth plus a 16th plus a 32nd plus a 1 over a really big number, right? What is the sum of all of those numbers? Right? That's what we're looking to try to do now, is how could I add those all up? And now, normally what we do is we just do it for just a couple of terms. You may even know the formula that you were just given back in Math 20-1. I want to show you how that formula was proven. So before I get there, I need to talk about just a couple of terms you're going to be asked about. The first one is convergent. The second one is divergent. You've heard these words before, maybe just from pop culture in the movie Divergent. totally different concept here. But I mean, the words make sense. If things converge, I'm like using my hands here. I'm bringing my hands together, right? Like when things converge, they come together, right? Hear me snap my hands together, right? Those are things that are coming together, right? Things that diverge are going apart from each other. They're not working together. So basically the concept here is that if a limit of adding up Sn, capital Sn is the sum of a whole bunch of continuing terms here, if you can add them all up together and that limit does exist, then for infinity, then it's a converging series. If not, then it's considered divergent. So I might ask you questions as to whether it converges or diverges. So let's try this question here. Is this going to converge or diverge? So just consider 1 plus 1 plus 1 plus 1 plus 1. Is this going to like limit out to a certain number where as I add 1 over and over again, it's I'm going to end up on a similar value? And the answer is no. As I keep adding 1 more, it just keeps getting bigger. This is not going to converge. This is diverging. I can't spell diverging. You guys don't need me to spell it. I'll just use C and D. This is diverging. Because what's happening, if you were to think of this graphically, is you have 1 plus 1 more gives 2, plus 1 more gives 3, then 4, then 5, then 6, then 7. This is not ending up at a certain number. It's just going to keep going on that trajectory for forever. Right? Whereas, consider this next one here. 1 minus 1 would give you 0. Then you add 1. Well, it would give you 1. Minus 1. No, that would give you, where was I at? 1 minus 1 gives you 0. Add 1 gives you 1. Minus 1 gives you 0. Add 1 gives you 1. Minus 1 gives you 0. Add 1 gives you 1. Is this converging on any one number? Now, I can't really draw this graphically the same sort of way, but this is really 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1. The sum of this really depends on where you're at. If you're at like a spot like this, it's 0. If you end there or there, it's at 0. But if you end on like this number or this number or that number, it's 1. So again, that's divergent. There's not really a limit that exists. But this is one we just did here. 1/2 plus a quarter plus an eighth plus a 16th. I mean, I'll just cheat and use a calculator for right now. We'll just try a couple of examples. Right? 1/2 plus 1/4 plus 1/8 plus 1/16. I'll stop there for now. That's 0.9375. Okay, well, let's keep going. Let's add the next number. That'd be 1/32. Okay. Then let's add the next number, 1/64. Add the next number, 1 over 128. Hopefully you see what's happening. This is getting really close to a number. That number is, pause for dramatic effect, that number is the number 1, right? As I keep adding these next numbers, if I add 1 over 512 and 1 over 1024, or whatever it is, that I'm not adding very much anymore. The amount that I add is very inconsequential, very similar to Zeno's paradox. Zeno's paradox is as you move the guy closer and closer, you moved him 1/2 and 1/4 and a little fraction more at a time. And eventually, by the time he's done, he has made it the whole way there. And he's made it the whole way there. In this particular example, it's equal to 1. Which means this is converging. This is converging on the number 1. So now that I've done a few other examples, let's talk about this next one. Well, what's happening here? Is this going to converge? Let's just try it in the calculator for a bit here. Let's take 9 and minus 3. And then add 1. And then minus 1/3. And then add 1/9. Okay, well, as I look at the previous numbers, there was 6, then there was 7, then there was 6.6, then 6.7 repeating. It looks like it might be converging on a number in that 6 to 7 range. Let's keep trying. What would the next thing be? I just finished doing an add, so I don't need to subtract. And then it looks like the pattern is I'm doing like a third of what I used to have. So 9 divided by 3 is 3, divided by 3 is 1. So anyways, 1/9. The next one is going to be 1/27th. So I'll subtract 1/27th. Right. Then I'm going to add 1, hopefully to the next number here, 27 by 3. Let's see, 27 by 3, that should be 81, I believe. 1/81st. Doesn't it look like it's converging on a number? Right, as I keep this pattern going further and further, I feel like it is converging on a number. It's getting closer and closer to about 6.75-ish in that range. So the question I have for us now is, can we combine all of this work we've been doing here, but now use the concept of limits to actually find this number? Actually find this number here. And I kind of have a proof here to begin with. What you're really looking to do here is take your first number, add to it that same number, but multiplied by your ratio. Add to that your same number multiplied by your ratio. Add to that your same number multiplied by your ratio. Really what you're doing is you're taking the limit as n approaches infinity for, like, say, a plus ar plus ar, and really what you're doing is you're adding it up until you get to the point where you have like ar to the n, right? Except n is infinity. You're just doing this over and over and over again, dot, 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 until the number that you're multiplying by, your 1/3 or your 1/2, you're doing that an infinite number of times, right? And so our proof here is that if this r value is less than 1, we already kind of know how this works, because we already know that a lot of these graphs, they kind of eventually converging on a number like this. What happens if r is not greater than 1? Well, didn't we kind of already talk about this a little bit further back here? Where was it here? Yeah, here it is. We already have this proof here, right? If this is, if your ratio is a 1/2 number, or a 1/3 number, or a 1/4 number, right? Then if this works like this, then it converges into a 0. That's a property that we can use, this one right here back there. Now it doesn't work, how I have this next slide kind of sitting here? It doesn't work if r is not less than 1, right? Because what ends up happening is you have a pattern where it's not converging on a value. It's probably like getting bigger and bigger, but this does work. So I want to show you this this formula here. Where is it here? Okay. So the formula that we would have had, I want to actually solve the proof right here, is a formula that you would have learned back in 20-1, and I even have it on the previous slide here. It is, I'm so jumping around, I'm sorry. It's this one right here. Sn equals a. Sn equals a. What's next here? 1 minus r to the n, 1 minus r. 1 minus r to the n all over, that's probably a little bit too big of a line. 1 minus r to the n all over 1 minus r. This is a formula that you would have learned back in grade 12 or grade 11 for how to sum up numbers. Now what I want to do here, though, is I want to attach a symbol here. Let's do it the limit as n approaches infinity. As n keeps getting bigger, as we let this r to the n become like an infinity number, and we get that far, let's see what happens now. So what we can do is, first I'm going to do a little bit of distributive law. I'm going to do a minus ar to the n over 1 minus r. I'm going to distribute out the a, right? I'm going to FOIL it across both of these. Then what I'm going to do is I'm going to apply my limit symbols to everybody. So, I mean, this seems a little bit silly to do because of what I'm going to do in a step later, but I'm going to do the limit as a, and then I'm going to minus the limit as n approaches infinity for ar to the n. And then these guys down here also get limits as well. Limit as n approaches infinity for 1, and the limit as n approaches infinity for r. Now at this point here, though, I remember what I know about r. That ratio had to be a fractional number, which means that I can apply a rule that I learned way back here. Sorry that I have to jump around a little bit. But the rule is, remember, if r is a number less than 1, and it's going to the power of n, it's equal to 0. Which means that right here, this guy right here, I could split up a little bit further if I wanted to, and I could even multiply it as the limit of a times the limit of n approaches infinity of r to the n. But all of this is equal to 0, which means that all of that guy is now gone. I don't need it anymore because literally this whole thing right here is going to become a 0. Well, because of that, I'm almost done actually, because now what I have is a whole bunch of constants. I have a constant here of a, my first term, but that's just a number. This would be like 2. Well, the limit of 2 as n approaches infinity is 2, so this just leaves you with a. The number 1 just stays the number 1, and r is just a number still. There's no variables left. So it ends up with this formula here. And maybe you recognize this off of an old grade 11 formula sheet. If you want to find the sum of a sequence that goes infinitely, here's the formula, a over 1 minus r. So maybe you've seen it written this way before here. It's s infinity equals a over 1 minus r. So I want to use that now on limit concepts here to solve a couple more questions, and then we should be done for our lesson. So let's do an example here. Let's find the limit of this right here. Well, all we have to use now is our formula. The limit of this is 1 over, no, it's not 1 over. It's a over 1 minus r. That's what it's equivalent to. That's our new rule. We can just go right to there. So a is your first term. That's 16. And then 1 minus r. Well, 1 minus r is 1 minus your ratio. What is your ratio? How do you get from 16 down to 12 down to 9? Well, hopefully, you're able to recognize that you're keeping about 3/4. To go from 12 down to 9, I believe it's 3/4, right? You times by 3, divide by 4. If you were to times this by 3, divide by 4, just do a little check here. 16 times 3 over 4 gives 12. Times by 3 over 4 gives 9. Right? Only it's not 3/4 though, it's negative 3/4, right? Your ratio on this one is negative 3 over 4 because you're flipping the positive negative signs. So here's what I'm looking for then. You've got 16 over 1 plus 3 over 4, right, with the double negatives, which really gives you 16 over 4 plus 3 over 4, which gives you 16 over 7 over 4. And then hopefully last step here, I'm skipping through a lot of basic arithmetic that hopefully you're familiar with. Again, this is a good place to ask me questions if I lose you on this step here. But this now gives you 16 times 4 over 7, which gives you 64 over 7. I now know what this thing seems to be limiting out to. Right? It seems to be getting close to 64 over 7. You know how I was doing this example a little while ago on my calculator? Let's just try this. If I were to, come here, calculator. There you go. If I were to take 16 minus 12, add 9, minus 27 over 4, add 81 over 16. And if I were to keep this pattern going here, it gets close to that number there, which if you kept the pattern going, should hopefully be really close to 64 over, what was it again, 7? 64 over 7. As I keep going, hopefully it should limit closer and closer to that value there. I want to make sure I just didn't screw my math there. It was 3/4, so 16, 1 plus 3/4, that's 4 over 4, that's 7 over 4. That means you times by 4 over 7. Yeah. Let's go back and actually try this example I was doing back here a while ago. Know how I left this one here? I was doing 9 minus 3 plus 1 minus 1/3. I even still have it in the calculator here, I believe. Well, let's do it again here. Let's rewrite it again here. We've got 9 minus 3 plus 1 minus 1/3 plus 1/9. Remember this one here? We thought it was getting close to about 6.7 or so as we kind of kept going, right? And then if I were to subtract 1 over 27 and then add 1 over, what was next, 81. Seems like it's getting close to like 6.75, somewhere in that range there. Let's try it using this formula now. So the formula is, if we wanted to make this go to infinity, 1a over 1 minus r. First term is 9. And it looks like my pattern is it's negative 1/3. My ratio is negative 1/3. So it means I need 9 over 1 plus 1/3, which is 9 over 4 over 3, which is 9 times by 3 over 4, which is 27 over 4, which looks like it's trying to get close to 6.75, which, look back at my calculator here. Isn't that what it seemed to be getting close to? If I keep the pattern going long enough, this is what it's diverging to. Think of that asymptote. This graph seems to be limiting out and getting closer and closer to, in this one right here, 27/4. And then same thing in this example right here. If I haven't done this one incorrectly here, if I keep this pattern going here, it looks like it should keep getting closer to 64/7. So, okay, there's a natural spot for me to remind you. Write down some questions if I lost you on stuff, because I'm going fast. I'm at 45 minutes here. I'm going to do my last example here, and then we'll call it a day. And you guys can ask me questions Tuesday, Thursday. Here's our last place. Let's do this task then. And this may seem, boy, this is like I've done this whole 45-minute lesson all to get to this point right here, and this may seem totally disjointed, where you wonder, what the heck? Where did this question come from? What does this have to do with anything? But I'm going to show you how the limit rules and the skills we've learned can help us express a decimal as a fraction. Now, some of you may already know how to do this in your calculator. Take 2.135335335. And then if you were to press the math fraction button, that may give you a fraction here. And we kind of know the answer going in. It hopefully is going to be 1057/495. But I want to show you how your calculator is doing that using calculus, because it's not, magic. It's using calculus to do this. So here's how we solve this question. And by the way, I should point out right now, you're going to get these on your assignment and on your midterm. So make sure you pay attention about how to do this one. So think of it like this. This is really 2.1. And then what you're doing is you're adding 35 thousandths. Right? Because isn't this right here, this is the tenths, the hundredths, the thousandths. So isn't that 35 there, 35 thousandths? And then what you're doing is you're adding another 35. You're actually adding 35, but now it's 100 thousandths. Because that's 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. And then after that, you need to add another 35. Only now we need 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 zeros. And really, I'm going to keep adding 35 of something here. Only it keeps getting bigger. Isn't that really what this number means? All right, if I lose you here, pause the video for a second just to ponder this concept. Right? But really, you have 2.1, and then you have 35 thousandths. You have 35 something morths, 35 something morths. What we really have right here then is a pattern. This is what I want to focus on here. Here we have a pattern. We have 35 thousandths, and then you're adding 35 hundred thousandths. We actually have a pattern here. What is my ratio? I'll just kind of pause for a second. I don't do a lot of wait time on videos, but maybe pause the video here just to think, what is the pattern about this part right here? What are we doing? And the answer is this. 1/100. You're dividing by 100 every time, or in a way, you're making the bottom of your fraction have 2 more zeros. So I can actually figure out this part right here. If I want to find the sum of all of this, I have that formula. Because it's going to go to infinity, the formula is a over 1 minus r. So this is equal to 2.1 plus the limit as n approaches infinity for, like, the way it's working here is it's 35 over, like, say, 1,000 times by 1/100 to the n. That's essentially what we have here. Just pause for a second to ponder this here. Your first term is 35 over 1,000. And then you actually are, I should actually say this is the sum of this. I need to have SN notation in there as well. You're doing as n approaches infinity for the sum of 35 over 100 times 1/100. And you're doing that over and over and over each time for n. But the good news is this guy right here, we just learned has a formula. It's it's a over 1 minus r. I seem to keep doing that wrong. So your first term in that portion of the series was 35 over 1,000. And your ratio was 1/100. Which means it's 2.1 plus 35 over 1,000. And then 1 minus 1/100th is 99 out of 100. Again, I'm just doing arithmetic here. So if I lose you on the arithmetic, rewatch, okay? Because I'm not going to be able to just talk you through every single little arithmetic step here. Hopefully you're able to kind of follow where that came from. Because the next thing I'm going to do here is I'm going to flip this fraction and multiply by the reciprocal. And what happens here is that this guy cancels with this guy. 100 and 1,000 can kind of cancel. And it gives you 2.1 plus 35 over 10 times 1 over 99, which gives you 35 over 990. Okay, at this point here, we're getting close to our answer, because we actually know our answer. I just had it on the calculator here. It's going to end up being 1,057 over 495. I'm not finished here. I have 2.1 plus 35 over 990. Now, I mean, just to pause for a second here. Look at this, 35 over 990. So that's going to give you, it's going to give you 0.035353535, like that, right? Which doesn't that make sense? Because the 2.1 is going to take, the 2 would go here, the 1 would go there, and that keeps going. So I just need to find a way to get the 2.1 into this. Now here's the better way of approaching that. Isn't 2.1, isn't another way of writing that as like, say, 2.1 over 1? Right? I mean, I can write it as a fraction over 1, which the reason why I want to point that out is another way of writing it is 21 over 10. This guy's actually 21 over 10. 21 over 10 is 2.1, which now means I can work on some common denominators. Because if this is over 10 and this is over 990, I just got to times this guy by 99 and this guy by 99 so that they're both over 990. So, I mean, I do need a calculator here. I wouldn't expect you to do this in your head. 99 times 21 gives you 2079. Now with common denominators, I can add them. So 2079 plus 35 gives me a sum on the numerator of 2114 over 990. And they're both divisible by 2. So if I were to take that and divide by 2, I can get to 1057. And if I've got 990 and I divide it by 2, I get down to 495. And look, there is that fraction. Wait, now that is a hard question. There's a big leap there in terms of what the skills you were just using. So I highly recommend rewatch that section there. And if I lost you on any of the arithmetic steps, kind of in between here where you're wondering, whoa, why did you just do this right here? If it wasn't clear the first time around, please make sure you make a note, okay? This is where you're going to discover this. At about this point here, the course is going to get a lot more challenging. I just due to the nature of me making these videos here, like I'm already almost pushing an hour in terms of time length here. I won't be able to give you 10 examples of everything, and I won't really be able to answer targeted questions, because if this is a classroom and I lost you somewhere, you could then say, oh, hey, right here, where did you go wrong? But I don't really know where any particular one of you is going to have some issues, like which step I'm going to lose you at. And so I just kind of have to make the example here and just go with it. And you guys need to make sure that you get a hold of me afterwards. I mean, right away, okay? Like, shoot me an email if you need. Make sure that we utilize Tuesday, Thursdays, or whenever you talk to me right away to help clarify things, because we're going to get to the point here where you get like one example, and I go through it the once in the video, and I don't really know where your struggles are going to be until you have them. So you have to make sure you watch these videos sooner than later. You can't be watching this video and it being like, say, Thursday before your assignments due. That'd be a poor choice. So I really hope that none of you are actually doing this on Thursday where your assignments due Friday. But so anyways, that's the end of my lesson. Like I said when I kind of started, this may seem like a bit of a strange section here. It's like, what did we even cover today? It was really a whole bunch of tangential type stuff, no pun intended, for limits. We were using limits in different and odd scenarios. So the three main things I need you guys to know how to do are you should know these rules here. You should know this one here, that's a rule, that 1 over n as it approaches infinity is 0, which I have highlighted here. There's another property here which says that r to the n is 0 so long as r is like a fractional value. You should know how to use those to solve certain questions. Like this one here is a good example. You're going to get lots like that on your assignment. And the last one is being able to use it to figure out converging and diverging series so that you can then try to figure out, in an example like this, how to take a decimal and turn it into a fraction. So it's a real hodgepodge today. It actually means that your assignment is quite large, because there's quite a few just random one-off questions here where I'm going to try to challenge you and see, can you figure out how to use the skills I've shown you to solve these problems? So, and that's what you're going to discover at the university level, is that I'm going to show you some stuff, but you're going to get questions that sometimes are similar, and you're going to get some that are those thinking kind of questions where, not that other questions aren't thinking, but the kind of questions where you really have to use what you've learned and show me that you can try to solve something new and unique and solve a puzzle that you haven't seen before. I have a friend who had a joke in university who said that explaining a joke is like dissecting a frog. You'll understand how it works, but it's dead. And I think that's kind of similar to some of these math questions here. Similar to explaining a joke. There's a puzzle here in a lot of these questions, and I need you to try to solve this puzzle. And I need you to resist the temptation to always just be asking me to give you the solution. It's like a riddle or a joke. Don't tell me, don't ask me to give you the answer to it, because that deprives you of the chance of working through it yourself and coming to your own aha moment. You can't ask for clues, okay? Don't feel like you can't ask me anything whatsoever, because you're going to want some clues. But I need you guys to be aware that you're reaching a point where you're going to start needing to struggle, and you have to learn how to persevere and how to plow through that wall that's in your way. You can't just go, I don't know, and give up. Like if you're spending 7 seconds on a question, you go, yeah, I don't know. Boy, you're not going to do well going forward, because you're going to have a lot of questions. I can think of my own experience in university in math, where I would be given an assignment and I'd be thinking about questions for, like, I kid you not, for like 2 or 3 hours, just trying random stuff, going, well, what if I try this? Will this take me anywhere? And then, finally I get up the courage and I go to my professor's office and I say, can you give me a hint or a clue? Like, what could get me started, right? So, anyways, I got off on a long tangent at the end here, a long diatribe about struggles here. But the advice I'd like to give you, I guess, 2 pieces. Please make sure you're watching these videos well in advance so you can ask me lots of questions in case I lose you, and leave yourself lots of time to think about some of these questions, because some will be familiar and some are going to be new challenges, and you're going to need some time to process. You won't be able to do this just the night beforehand anymore. If you try to, you probably won't do very well. So. Okay, let me sign off. This is 57 minutes at this point here, which is about the most I want to let it go. So email me, get a hold of me, however it is your method is, and let's talk. Okay, we'll talk to you later.